This is a really fun problem. So the setup for this is that we have a cart sitting on frictionless small wheels, and we're taking some kind of air cannon, like a t-shirt cannon, and shooting 2 kilogram balls of clay at this cart. And we're just going to keep shooting and shooting and shooting, and they build up on the back of the cart, as you can see in the picture. So the cart is increasing in mass as this occurs, one inelastic collision after another. And it keeps speeding up, but it does so more slowly over time because its mass is growing. So we're going to try to find the general solution for this. By the time we get to part C, we want to find the speed after we shoot n balls at this sled. And then in part D, we're going to apply that formula to figure out how many times do we have to shoot this thing to make it so it speeds up to 8 meters per second. So A and B are really warm-up questions. Can we solve these inelastic collisions and find the speed of the cart after the first couple clay balls, stick to it, and then hopefully we see a pattern and we're able to express this sequence explicitly in terms of n. Of course, these are little momentum conservation problems, so P initial equals P final. In my initial state, I have this 2 kilogram clay blob moving at 10 meters per second. In my final state, I'm going to have clay stuck to this cart, so it's going to be 52 kilograms times V final. And I'm going to write one step in between here because, after all, our goal here isn't just to get a number. We're trying to recognize a pattern. So I end up with 2 times 10 divided by 52. All right, now I'll get the number just so I can answer the question. And I get 0.385 meters per second. Okay, let's shoot another ball at this thing. So again, it's momentum conservation. But now in my initial state, I have 2 objects moving because the cart has started to move after the first impact. So I'm going to have a 2 times 10 for the mass of the clay blob and the speed of the clay blob, plus the cart with 1 clay blob stuck to it, that's 52 kilograms, times its speed, which I'm going to put in again without using decimals because I'm trying to recognize a pattern here. And then in the final state, I'm going to have the cart with 2 blobs stuck to it. That's 54 kilograms times some V final. And things clean up here on the left, and I end up with 20 from the clay blob I just shot, and the 20 from the cart that was slowly moving after the first impact. So on the left side here, I'm really just showing how much momentum I'm adding up total. On the right side, I have the total mass and final velocity. So 20 kilogram meters per second from the first shot, 20 from the second. And this time I end up with a 40, or maybe I'll write it as 4 times 10 over 54. When I run the numbers on this, I get 0.741 meters per second. And I want to point out that that's a little bit less than double the answer we got from part A. So we added just as much momentum to it, but the mass had grown larger, so it's a little bit less than twice as much. So that's what I mean by the growth rate and the speed slowing down over time. So part C, I want to get a general formula after the nth ball sticks to the sled. And I think it would be wise to look at the third impact before we try to generalize. So again, P initial equals P final. And in my initial state, I'm going to have a clay blob flying at the cart, 2 times 10, 2 kilograms times 10 meters per second. And I'm going to have a 54 kilogram cart moving with this final speed of 4 times 10, or 40 over 54. In my final state, I'm going to have 56 kilograms moving with some V final. So on the left-hand side now, I have 6 times 10. Again, it's really just a way of tabulating how much momentum I've added to this cart. It's 60 kilogram meters per second. And I get V final is 6 times 10 over 56. So I think I see the pattern now. I had 2 times 10 over 52, 4 times 10 over 54, 6 times 10 over 56. So now I can write V as a function of n. So stepping up from 2 to 4 and then 6, that's a 2n. And there's a 10 there in the numerator. And then stepping up from 52 to 54 to 56, that's a 50 plus 2n, where n is equal to 1, 2, 3, and so on. Anytime you write down a sequence like this, you should double check by plugging in those numbers to make sure you get the list that you were supposed to. So plugging in n equals 1, I get 2 times 10 over 52. Yep, that works. Plugging in n equals 2, I get 4 times 10 over 54. That works. And n equals 3 works as well. Now in the question here, I said you can verify your formula makes sense by taking the large n limit. So I'm going all the way to where I've shot infinity balls of clay at this thing. What's going to happen? So I want to figure out on a physical intuition basis what should happen, and I'm going to take the limit to verify it does happen. So this cart just keeps speeding up and speeding up and speeding up, and it does so slower and slower and slower and slower because its mass is growing and growing. So what's the limit to this process? The limit is when the cart is approaching 10 meters per second. It's going to get to the point where those clay balls can't catch up anymore. So absolutely, it can't go faster than 10. When I take the large n limit, I'm going to go ahead and simplify the numerator to 20n. There's two different approaches here. In a calculus class, you might be asked to divide the top and bottom by n, and then take the large n limit, and that's one way to do it. In a physics course, it would be more normal to just say in a sum or a difference, the largest power of n is going to dominate, and what I'm looking at is the denominator here. When n becomes extremely large, does the 50 matter anymore? There's no way. If I think n is 1,000,000, then the 2n would give me 2,000,000, and the 50 would be a negligible correction. So in other words, in the large n limit, that 50 is irrelevant, and I cross it out. Now I can simplify inside my limit, and the n's cancel, and I get 20 over 2, which is 10. And I've verified that in the large n limit, I'm going to get a velocity of 10 meters per second on this cart. Okay, let's look at part D. Compute the number of balls it takes for the speed of the cart to exceed 8 meters per second. So what I'm trying to do is solve for n, where I have my speed as a function of the number of balls, 20n over 50 plus 2n. And I'm saying the speed has exceeded 8 meters per second. So I have a little inequality to solve. Multiplying both sides by that denominator, I get 20n greater than 8 times the quantity 50 plus 2n. Distributing the 8, I get a 400 plus 16n. So I'm going to subtract the 16n from both sides. So I get 4n is greater than 400, which means n must be greater than 100. So after we shot this thing with 100 2-kilogram blobs of clay, and I want to point out here that means that the total mass there is 250 kilograms, is getting enormous. It would be moving at exactly 8 meters per second. So technically the correct answer for the number of balls to exceed 8 meters per second would be 101. If you find the physics content on Zach's Lab helpful, click on the Zach's Lab logo on the right to browse playlists and subscribe to the channel. I produce over 100 new videos per month, and subscribing is the easiest way to find new content. Thanks for watching.